also, as part of this unit, we're going to be working with equations that have radicals. The word radical refers to the square root. And something that happens when you use algebra to solve for radicals is you sometimes end up introducing extraneous solutions. Extraneous in this context means that they're not actually solutions. They appear to be a solution, but if you plug back into the original equation, the value won't satisfy the original equation. So let's look at how that happens. So if I'm going to solve this equation, I need to isolate the x's. So a natural thing to do would be to square both sides, but let me rewrite it the way that it looks right now. So if I square both sides, I'll get x squared, and then when I square the square root, they undo each other. Excuse me. And now I can group together all of the x terms. So x squared plus 6x. Well, if I have them equal 7, there's nothing very obvious that I can do here that's going to help. So instead, let's put all the terms on one side so that it looks like a quadratic in standard form. And you could use the quadratic equation, but let's please not. Let's factor. So hopefully you recognize this as something that is easily factorable. Let's see. The only factors of 7 are 7 and 1. So I know that those have to go here because they have to multiply to become 7. How can I make those equal 6? If I add 7 and subtract 1, now when I multiply it out, I'll have subtracting 1, adding 7 is positive 6, because the positive is attached to the 7, and then I'll subtract 1 from there. And when I multiply those two, the negative 7 ends up negative. Okay, so that implies that x is negative 7 or x is 1. But let's substitute into the original equation and see if both of those answers work. So if I substitute in, let's do negative 7. So is it true that negative 7 equals square root of 7 minus 6 times negative 7? Okay, so because I have a negative sign here, let's distribute, or let's have those undo each other. So I've got 7 plus 6 times 7 is 42. So 7 plus 42 is 49. Square root of 49 is positive 7. So negative 7 is not equal to positive 7. So so negative 7, even though we got it as a solution to this squared equation, isn't a solution in the original equation. Let's try 1. So is it true that 1 equals root 7 minus 6 times 1? Well, yes. So 7 minus 6 is 1. Square root of 1 is 1. So that one works. So x equals 1 is the only solution. All right, so where did the extraneous solution come from? I guess here's one nice way of looking at it. If I have x equals root 7 minus 6x, this part must be positive because the output of a square root is always positive. So because that's equal to x, we know that x cannot be negative. Okay, well, what happens? So that's the original equation. What happens if I square both sides? If I square both sides, this is the same equation in a certain sense. The whole idea of algebra when you do the same thing to both sides is if both sides were equal before and you change them in the same way, they must still be equal afterwards. But there's a subtle difference here because now x can be positive or negative. Because as soon as you plug in a negative value to x, squaring it makes it positive. So what that means is that any negative solutions to this equation won't work if you plug them into the original equation. So won't satisfy the original. And that's where the extraneous solutions come from. In the process of squaring, you introduce new values that would make the squared equation true that don't make the original equation true. So what can you do? I mean, you don't want to not square things because sometimes you need to do that algebraically in order to isolate x and solve. What you do is this. So you always check. And when you always check, that's like a surefire way of knowing whether your values satisfy the original equation.